First of all, I would like to thank the organizers for inviting me. It's a great pleasure to speak at this conference. So in this talk, I'm going to discuss the problem of global well-posedness for the derivative nonlinear Schrödinger equation. It will be a joint work with Hajer Bahouri. So, that's okay. So the equation I'll be interested in is this one. I'm going to consider it's on the circle subject to some initial condition U0 in some Sobolev space HS. Also, I'm interested in the periodic case. As we will see, the things I'm going to describe will be closely related to what happens on the real line. So in fact, at the beginning of my talk, I will speak of both cases simultaneously. The remarkable feature of this equation is that it's completely integrable in the sense that it meets a Lax-pair formulation, and as a consequence, an infinite number of conservation laws, and for suitable initial data on the real line can be integrated by the inverse scattering method. The integrability structure of the Dirichlet equation was discovered by Kaup, Newell, in 1978. And since then, this model, and in particular the questions of its well-posedness, have attracted a lot of attention. Concerning local well-posedness in the Sobolev spaces HS, for S, S greater than or equal to 1/2 on the real line, the well-posedness is known by the work of Takaoka in 1999, and on the case of the circle by the work of Kerr in 2005. These works use only a PD method, so they pass at some point by a fixed point argument. As a result, the obtained solution are locally uniformly continuous in initial data, and even better, they are analytic. From this point of view, these results are optimal because it is known that for S less than 1/2, the data to solution map cannot be uniformly continuous. On the other hand, if we look on the scaling, we see that the Dirichlet equation is invariant with respect to the scaling you see here, which preserves the L2 norm. So the equation is L2 critical. This means that in the scale of the Sobolev spaces HS, we have a gap of 1/2 derivative between locally uniformly continuous well-posedness and the scaling critical regularity. This gap can be closed by leaving the scale of Sobolev spaces HS and working in more general Fourier-Lebesgue spaces, and on the real line this was done by Grunrock, and on the circle there is almost optimal result by Deng, Nahmud, and Yu, improving on the previous results of Grunrock and Herr. Well, returning to the scale of of the Sobolev spaces HS, S1 equal to 1/2 is still not the end of the story, because one can go below, but with a flow which is not locally uniformly continuous on initial data, but just continuous. And I will mention the corresponding results, but a little bit later. Let me first of all say some words about the global well-posedness. So as soon as we have local solutions, the standard way to globalize them is to use the conservation laws. Here we have plenty of them because the equation is integrable. In particular, one has an infinity of polynomial conservation law, which are polynomial in U and derivative of U. They can be ordered by scaling, and the three first of them you see here. One has a conservation of the mass, while one has the conservation of these quantities that I will call momentum and not by P of U, even if for the Dirichlet equation is in fact it's Hamiltonian, so it's in fact the energy. And then one has a conservation of this E of U that I will call energy, but in fact it's the second energy. And it turns out that using just the conservation of these three quantities, one can obtain global well-posedness for the masses strictly less than 4 pi. on the real line, and in the H1 setting, this was a result of Wu. And later on, this result was extended to H1 half over R by Guo Wu. And the point here is that if the mass is strictly less than 4 pi, then H1 norm of solution is controlled by the momentum and the energy, thanks to the inequality you see here. So this inequality gives the control of the L6 norm of U, but as soon as you control L6 norm of U, you control the L2 norm of the derivative as well, because of, again, of the conservation of E of U. And this inequality in its turn is a consequence of the Gagliardi-Nirenberg inequality, this one, that gives the control of the L6 norm in terms of the L4 norm and L2 norm of the derivative. And one has a similar result on the torus. In the H1 case, this was done by Mosinket and Och, and later on it was extended to H1 half by Mosinket itself. It happens that this bound 4 pi for the mass, it's not something artificial. There is something happens at this level, namely the conservation laws lose their coercivity. The simplest way to see it on the real line is to consider the solitary wave solutions of the Dirichlet equations that you see here. So one has explicit solutions of this form, where the profile phi depends on two parameters E and C, and given by this expression, well, it's easily to see that this is a C-infinity function that decays exponentially at infinity. Now, if we fix a C positive and send E to 0, then this solution that you see here, it reduces to the one which is written here. This solution that you obtain in the limit E goes to infinity, E goes to 0, decays only as 1 over y, but still it's a nice solution that belongs to all Sobolev spaces. It's so-called algebraic solitons. And if we now look on the mass of the algebraic soliton, we find that it's equal to 4 pi, and all the other polynomial conservation laws vanishes. So it means that we can, in principle, control the size of HS solution by the polynomial conservation laws. Because for the algebraic soliton, if you take C large, the Sobolev norms with S positive are large, and conservation laws does not see this thing. It happens that one has, in the periodic setting, one has also an analog of the periodic of the algebraic soliton. These solutions that I denote by UN here, they're given by this expression where Vn is this thing. Well, it's, I don't know, is it visible, but still it's a periodic function. And if we compute the mass, again, we find 4 pi. And all other polynomial conservation law vanish. And as n goes to infinity, in fact, this solution becomes close to the algebraic soliton. For the next equation, the conservation laws in principle can't allow to exclude the possibility of finite or infinite time breakdown. In particular, can't exclude the possibility of concentration of the algebraic soliton. Still, it happens that by now we know that this thing does not happen, at least on the real line. And the first evidence for the fact that global existence persists for large masses was obtained by inverse scattering method. There is a lot of work where the global existence for the Dirichlet equation on the real line was investigated by the inverse scattering method. The most definite result was obtained by Catherine with her co-authors. It was a result that saying that the Dirichlet equation is globally well posed for any initial data in the weighted Sobolev space H22, which is a space of the functions that belong to H2 and belong to L2 with this weight x squared. Probably this space is not completely optimal. Well, Catherine will correct me if I am right. But some localization is absolutely necessary if we would like to use the inverse scattering methods, because even to define the objects that enters in this method, you need that the solution you need the solution to be in L1. Of course, the force of the inverse scattering method is that it's not only give the global existence, they also allow to obtain, describe the asymptotic behavior of solutions at infinity, and namely to prove the Salpon resolution conjecture. Now, if we go to the Sobolev spaces without weights, global existence in HS with S greater or equal to 1/2 was proved at some point by Hajer and me. And our result is also relies on the integrability structure of the Dirichlet equation, but without using the inverse scattering method. In fact, the only thing that we use is a conservation of the transmission coefficient that remains well defined for HS solutions, provided we stay away from the essential spectrum. This idea itself is not new. I don't know the exact chronology, but it was already present in the works of the Alexei Rybkin, Monica Vizan, Roland Kilip, also in the work of Daniel Tataru and Herbert Koch on the low regularity solution of the NLS MKdV equations. The difficulty of the NLS equation is again that this transmission coefficient is not coercive. Well, as we'll see, for the algebraic solitons, it's identically equal to 1. So one has to add some additional arguments. Okay, and later on, Benjamin Harrop Griffiths, Ron Kilip, Maria Nitkum, Monica Vizan succeeded to go down to the critical space L2. And this was done by the method of the commuting flows. Of course, here the flow is not locally uniformly continuous, but only continuous in initial data. Let me also mention that they have done a work on the circular well, where they applied this method to prove global well-posedness of the Dirichlet equation in HS for S greater or equal than 1/6, under the restrictions that the mass is strictly less than 4 pi. Well, to summarize, on the real line, the things are relatively well understood, but on the circle, the situation is less clear. To the best of my knowledge, global existence for large masses is not known even in the case of C-infinity solutions. And in this talk, what I'm going to discuss is a recent result that we obtained with Hajer that allows to replace the bound 4 pi by 8 pi. So it's the theorem that you see here. It says that the Dirichlet equation is globally well-posed in H1 on the circle, provided that the mass of solutions is strictly less than 8 pi. And furthermore, the solutions remains bounded in H1 uniformly with respect to initial data on the bounded sets of H1, in the sense that for any R positive, any delta strictly less than 8 pi, one can find a constant C, so that for any initial data with H1 dot norm less than R and the mass less than 8 pi minus delta, the solution, as H1 norm of the solution remains bounded by this constant C. The fact that we are in H1 here, it was our choice, just to avoid the technicalities. And we hope that our argument can be adapted to HS with S at least greater than 1/2. And we also hope that our argument can be adapted to any mass. And it's a work in progress. We currently can replace 8 pi by 12 pi, but we hope that at some point we'll be able to get rid of this restriction at all. So in the remainder of my talk, I'm going to give some ideas of the proof of this theorem, staying with the bound 4 pi, because even to go from 8 pi to 12 pi is, is technically more involved. As in the case of the real line, the proof of this theorem relies on the integrability structure. So let me start by introducing the corresponding spectral objects. And in fact, we will need these objects in both geometries, on R and on the real line, which is not very surprising. So as I've mentioned, the integrability structure of the Dirichlet equation was discovered by Kaup-Newell, who remarks that the Dirichlet equation can be viewed as a compatibility condition of this system you see here. So here psi is a function of t, x, and lambda. It takes the value on C2. Lambda is a complex parameter which does not depend on t and x. Sigma 3 is this Pauli matrix, and capital U is this ith-diagonal matrix. And it's an easy computation to check that small u solves the Dirichlet equation if and only if this compatibility condition holds. As is usual the case for the integrable equations, the spectral problem defined by the first equation will play an important role for us. So let me rewrite it in the following form here. LU of lambda psi equals 0, where LU of lambda is this operator. If you look carefully, you see that this spectral problem has a structure similar to the Zakharov-Shabat system that arises in the Lux formulation of the cubic NLS, except that the spectral parameter here we have lambda square instead of lambda, but this is not important. What is more important is that, What is more important is that lambda enters also in the potential. It is also important to mention that for lambda imaginary, you see that the problem is self-adjoint, as for the defocusing cubic NLS. And for lambda real, the problem in fact has the same symmetries as the Zakharov-Shabat system for the focusing NLS. And as I already said, we will need to consider this spectral problem in both geometries, on the real line and on the circle. And let me start by the case of the real line, assuming that our potential is an L2 over R. Then for lambda, with imaginary part of lambda square strictly positive, one can introduce two Yost solutions that I denote by psi plus u, psi minus u. They are defined by the asymptotic at infinity. Psi minus u is a solution that decays as e to the power minus I lambda square x times the vector times the vector 1, 0 as x goes to minus infinity. And psi u plus decays as e to the power I lambda square x times the vector 0, 1 as x goes to plus infinity. These solutions are analytic function of lambda in this region that I denote by omega plus, you see it here. And therefore, if you consider the Wronskian, which is I denote by AU of lambda, it's also a holomorphic function of lambda in omega plus. And furthermore, because of this property, it's an even function of lambda. And the key point is that this function, AU of lambda, is preserved by the Dirichlet flow, in the sense that if we now switch the time dependence, assuming that u is a solution of the Dirichlet equation, then the function AU of t is time independent. So let me describe some properties of this object, because it will be important for us. First of all, the Dirichlet scaling translates to this function a by this relation. Next, if we consider the zeros of a of u in omega plus, they are just the eigenvalues of the Kaup-Newell spectral problem, and dynamically they correspond to the solitons. For one soliton solution that I have written, the function a has this form. So you see that it has two simple 0 plus square root of zeta EC minus square root of zeta EC, with zeta EC is this, given by this explicit expression in terms of the soliton parameters. If we now send e to 0, keeping c positive, we recover the function a corresponding to the algebraic soliton, which identically equal to 1. So this is the main difficulty of the Dennys equation. This function a, which is the inverse of the transmission coefficient, does not see at all the algebraic soliton. So we have the same a as for the Euro potential. Still, the algebraic soliton is not completely transparent from the spectral point of view. There is a spectral manifestation, namely the corresponding spectral problem has still two eigenvalues, plus minus I square root of c over 2, that control the size of the soliton, but they are embedded. So you see this picture. They're on the imaginary axis, so they are embedded, and therefore they are difficult to control. So this is a problem. I have assumed that the potential u is L2 function, but if we now assume that it's better, say it's rapidly decaying at infinity, suppose u is just Schwarz function, then the function au extends as a C-infinity function up to the boundary of omega plus, and on the boundary one has these properties. At 0 it equal to 1. This is immediate from the form of our spectral problem. On the imaginary axis, modulus of A is greater or equal to 1. So as for the defocusing in LS, and this is normal because here we are self-adjoint. And on the real line, the modulus of A is strictly less than 1 as for focusing in LS. And at infinity, AU of lambda tends to this exponential. And we have even better AU of lambda. It means a complete expansion in inverse powers of lambda as lambda goes to infinity. Since A is even function of lambda, it's convenient to consider AU of square root of zeta, that I will denote by AU tilde of zeta, and then to consider its logarithm. Then for logarithm, we have an expansion of this form, where the coefficient are polynomial and u and derivatives on u. And of course, since the function a, and therefore a tilde, are preserved by the Dennys flow, these coefficients are conserved quantity, and this is precisely our polynomial conservation laws. Namely, if we consider E0, E1, E2, we recover up to a constant, the conservation quantity I have written in the beginning. And furthermore, if we take zeta real and consider modulus of a tilde squared minus 1, this is a Schwarz function. Well, there are different possibilities to recover this behavior at infinity, but one of the possibilities to transform the the Kaup-Newell spectral problem to a standard Zakharov-Shabat system. There is an explicit transformation that allows to do this, and then apply well-known results for the Zakharov-Shabat system. Now if we look on the function, this function a tilde u of zeta, this function is allomorphic function in the upper half plane, and therefore these coefficients ek of u can be expressed in terms of its zeros in upper half plane and the traces of a tilde at infinity. I have written the corresponding formulas here, assuming that the function a tilde does not vanish on R plus. In this case, one has only a finite number of zeros. So if I denote them but zeta j, well, we count them with their multiplicity, then one has these trace formulas for all k greater or equal to 1. And one has also a similar expression for the mass you see here. And in this expression, both contributions, the contribution of the zeros, so of the eigenvalues, and the contribution of the trace of a tilde on the real axis are positive. So the mass controls both things. And this was an important point, crucial point in our work with Hajer on the real line. And in particular, this trace formula shows that if we look on the angles of this form, there is always a finite number of zeros, and furthermore, we have this bound for the number. So in my trace formulas, I suppose that U is a Schwarz potential, but in fact, this bound extends just to 2L2 by continuity of the function A with respect to U in L2 outside the spectrum. Okay, so this was on the real line. Now let me say some words about the periodic case. So now I assume that the potential is a T-periodic function which belongs to L2. In the periodic case, the central object is a monodromy matrix that I denote by mu of lambda. If we introduce the fundamental solution of our spectral problem, this EU of lambda, then the monodromy matrix is just the value of EU as x equal to capital T. Clearly, the monodromy matrix is an entire function of lambda with a determinant equal to 1. If furthermore, we have these symmetries that you can see here, and also the scaling. Now, if we switch the time dependence, assuming that U is a solution of the periodic solution of the Dennys equation, then the monodromy matrix itself is not preserved by the Dennys flow, but its trace that I denote by delta U of lambda, its so-called Flaquet discriminant, is preserved. And the values of delta for the values of lambda for which delta is equal plus minus 2 corresponds to the eigenvalues of the Kaup-Newell spectral problem with periodic boundary conditions in the case of the plus 2 and anti-periodic boundary conditions in the case of minus 2. And since the Flaquet discriminant is preserved, the periodic and anti-periodic eigenvalues are preserved as well. We will need also to consider the Dirichlet-Neyman eigenvalues. So the Dirichlet eigenvalues are the eigenvalues of our spectral problem with the boundary conditions that you see here. And Neyman eigenvalues corresponds to the boundary condition where one changes minus to plus. So these eigenvalues are zeros of these two functions that you see here, ADU in the case of the Dirichlet eigenvalues and A and U in the case of the Neyman eigenvalues. These functions are not preserved by the Dennys flow, so the Dirichlet and Neyman eigenvalues can move, but still they will be important for us, and again, this is normal. Now, as the function, the spectral coefficient AU of lambda in the case of the real line, the Flaquet discriminant generates the polynomial conservation laws by its asymptotic at infinity. More precisely, assuming that the potential is C infinity, one has this complete expansion in inverse powers of lambda, where the coefficient are again our polynomial conservation laws. Let me mention that in the case of these particular solutions that I have written, UN, that are periodic analogs of the algebraic soliton, the Flaquet discriminant is just 2 cos lambda square as zero potential, for zero potential. So this shows that all other polynomial conservation laws vanish. So here the potential is assumed to be C infinity. Now, if it's just H1, we can't write the complete expansion, but still we have something, and so the corresponding asymptotics are written here. And we have a similar thing for the functions ADU, A, and U, but a slightly worse remainder. Here we have lambda squared, and here we just have lambda. Well, these asymptotics will hold uniformly with respect to U in bounded sets of HM1. And from this, we see that if we consider large periodic, antiperiodic Dirichlet or Neyman eigenvalues of our spectral problem, then up to translation by 1/2 of the mass in lambda square, they are close to the corresponding eigenvalues of the unperturbed problem. And if we now combine this property with the symmetries that we have for our functions delta u, a, d, u, a, and u, which is given here, we can deduce the following property, which will be absolutely crucial for us in the proof of the theorem I have announced. So this property is given by the lemma that you see here. So in this lemma, one works in the H1 setting and consider continuous deformation of the potential preserving the Flaquet discriminant. Namely, suppose we take u0 H1 function on the circle and we deform it continuously in H1, preserving the Flaquet discriminant. So the deformation is this u. It's a continuous function on the interval 0, 1 with values in H1 that coincides as tau equals 0 with u0, and such that delta u tau is equal to delta u0 for all tau. Then the lemma says that for all gamma positive sufficiently small, say less or equal to p over phi 4, one can find an integer n0, a large integer that depends only on gamma and on h1 norm of the u0. This will be important, such that for all n less or equal minus n0, the interval En, this is an interval of the imaginary half-axis R plus, defined in this way, by this lambda n plus minus. This interval contains at least one Dirichlet eigenvalue and one Neyman eigenvalue for all tau. So you see the picture, so the interval En is here on lambda plane. And if we now introduce zeta, which is equal to lambda square plus 1/2 of the mass, note that because we suppose that the discriminant is conserved, the mass is conserved as well, so we can just, so this is equal to 1/2 of the mass of u0. Then the interval becomes a gamma neighborhood of the point Pn, so the multiples of pi. This result, as I have said, is a direct consequence of the asymptotics of our spectral functions and the symmetries, because as for u0, choosing this n0 sufficiently large because of my asymptotics and symmetries, I can be sure that each interval En contains exactly one Dirichlet eigenvalue and one Neyman eigenvalue. If we now start to deform u0, then the eigenvalue can move. But the point is that they can't cross the ends of the interval. The points lambda n plus lambda n minus here, they are forbidden for the Dirichlet and Neyman eigenvalues, because if we consider the Flaquet discriminant, it's tau independent. So for n sufficiently large, if we choose n0 sufficiently large, this absolute value of this discriminant will be less or equal to minus delta. And because of the self-adjointness of our spectral problem, this shows that the functions a du and a and u can't vanish in this point lambda n plus minus. So the eigenvalues can't cross the ends of the interval. And this means that the only way for them to move, to enter the interval En or exit is in this way. And they can do it only by pairs because of the symmetries. So this means that the number of the Dirichlet and Neyman eigenvalues in the interval En is not conserved by the parity, is conserved. And since at the initial moment we have exactly one of each of them, in this interval there is still at least one of them. Well, once more, this will be important for the proof of our theorem. Well, now I have everything to start to explain the proof. I don't know how far I will be able to go, but still. So the beginning follows the beginning of the proof in the periodic case follows closely the things we have done on the real line. First of all, by the local well-posedness theory, in fact, the only thing we need to prove is the bound. Furthermore, it's enough to prove this bound on a dense set of initial data, say C infinity initial data. So we just need to prove that for any R positive and any delta positive strictly less than 8 pi, we can find a constant C such that for any initial data bounded by R in H1 and with mass strictly less than 8 pi minus delta, the solution remains, as soon as it exists, remain bounded in H1 by C. And this we are going to prove by contradiction, assuming that we can find a sequence of initial data, a C infinity initial data U0n, bounded in H1, and the sequence of time Tn such that if we consider the solution Un corresponding to the initial data U0n at time Tn, this gives us a sequence which is unbounded in H1, that the H1 norm dot, H1 norm of Un of Tn goes to infinity, Sn goes to infinity. And of course, we can always assume that the mass of U0n has a limit Sn goes to infinity that I denote by small m. Well, in our case, the small m is will be strictly less than 8 pi, but for the time being, I can keep this small m arbitrary. Well, as soon as we have this Un of Tn that goes to infinity in H1 dot, we rescale them to produce something bounded in H1. I denote the rescale profile by capital Un. The scaling parameter is chosen in this way. And if we do so, we get capital Un, which is C infinity, mu n periodic, with the mass equal to the initial mass of U0n, and with H1 dot norm on the distorted torus equal to 1. And then the idea will be the same, general idea is the same as in the case of the real line. We are going to analyze carefully the profile decomposition of this capital Un with respect to the Sobolev embedding of H1 to LP with P strictly greater than 2, and to show that this profile decomposition has very special properties, so very special that, in fact, this thing can't exist. Since our profile, capital Un, is mu n periodic, before running the profile decomposition, it's convenient to put the profiles into H1 over R. If we do this by constructing a sequence that I denote a sequence Vn, which is, so all Vn will be C infinity compactly supported. And more precisely, we have Vn is supported in the interval minus Rn mu n plus Rn, where Rn is a fixed sequence that goes to infinity, but much slowly than the period mu n. So mu n divided by Rn is also goes to infinity. Next, so our Vn are restricted on the interval 0 mu n, so on the period coincides with the periodic profile, or translated eventually by something that I denote by Yn. And also we do the things in such a way that if we consider the H1 norm of Vn in Rn neighborhood of 0, so here, and mu n, this thing is small. In particular, so this gives us a bounded sequence in H1 over R with energy that goes to 0. This Vn is very easy to produce. It's sufficient to truncate capital Un on the interval of the length mu n plus 2 Rn, putting the truncation function at scale Rn in the places where Un is small. And then this is done. We are done. Now, as soon as we produce this Vn, we show that the profile decomposition of this sequence with respect to Sobolev embedding of H1 over R to LP over R has the following structure. So this proposition here, it says that we can find there is a finite family of non-zero H1 profiles WL. Such that for all profiles, the corresponding function A tilde is identically equal to 1, and such that up to passing to eventually to a subsequence, Vn can be written as the sum of translated profiles WL plus a remainder Rn, that goes to 0 and h1 dot Sn goes to infinity. Furthermore, the profiles are well separated in the sense that the distance between y and L and y and k goes to infinity for all L different from k. And furthermore, they are well localized inside of the interval 0 mu n, in the sense that y and L and mu n minus y and L goes to infinity for all L. And furthermore, the number of the profile is bounded by m divided by 4 pi. And well, this bound itself is in fact an immediate consequence of this property that says that the A tilde function of all profiles is identically equal to 1, because I recall you that we have said that at least for Schwarz potential, A tilde u at 0 is equal to 1, and at infinity one has this asymptotics. And in fact, this property remains valid for L2 potential in the sense if we consider zeta in the angles like this, or avoiding the essential spectrum, then the limit of A tilde u zeta as zeta goes to 0 is equal to 1, and limit of A tilde u zeta at infinity is equal again to this exponential. And this means that if you have a potential WL that for which A tilde is identically equal to 1, it automatically implies that its mass is a multiple of 4 pi. And if it's exactly 4 pi, that we can identify this WL with an algebraic soliton. So returning to our profile decomposition, so this gives us this bound starting from this property. Well, I'm not going to discuss the proof of this decomposition here. It's an adaptation of the arguments that we have used in the real line. In the case of the real line, the proof relies on the conservation of the function A tilde. Here, of course, the function A tilde corresponding to the potential VL is not a rescaled A tilde of the initial data, but still we have the conservation of the Fouquet discriminant instead. We also very careful with our truncation function. We put them in the places where the potential capital UN is small. So this is enough to make the things work. Now, for the moment, my M was arbitrary, but if I now recall you, if I now assume that M is strictly less than 8 pi, then this becomes strictly less than 2, so there is only one profile in this case, with the mass equal to 4 pi, and so it's an algebraic soliton. So in the case of masses strictly less than 8 pi, this profile decomposition reduces to a very simple thing that you see here. So Vn can be written as a translation of an algebraic soliton W with some parameters C gamma plus a remainder that goes to 0 in h1 dot as n goes to infinity. And furthermore, the algebraic soliton is well localized inside the interval 0 mu n in this sense. And also, if we consider now the mass of the remainder, we see that it's equal m minus 4 pi plus small o of 1. So it's strictly less than 4 pi now, and this will be important. Okay, so as soon as we prove this, the next step will be to return on the construction of Vn and to refine it, because the problem is that we have to be very carefully with our truncation functions, and very carefully also with the place where I put them. And the point is that at this stage we don't know yet how carefully we should be. So we introduce an additional parameter that will be known by K. That will be large, so greater equals than m squared, say with m a fixed constant, large fixed constant, still much smaller than mu n in the sense that less or equal than mu n times m minus 2. And then for each n and each k, we construct a family, a profile Vnk with the following property. For the profile Vnk sin-infinity function, compactly supported with support in the interval minus m mu n plus m. As before, on the interval 0 mu n, it coincides with the translation of the original periodic profile capital Un. Now the translation parameter might depends on k. Next, in H1, our function is 1 over square root mu n small in the M neighborhood of 0 and mu n. So my picture is not good, but still in red. So this is M neighborhood of 0 and M neighborhood of mu n. Here our function, H1 normal of the function is for the 1 over square root of mu n. So this is not, this doesn't depend on k. So the k appears only in the last property. We ask our v and k to be also small in the neighborhood of the size mu n over k. And so the neighborhood of 0 and mu n of the size mu n over k. Small in this sense. So in principle, k is, this is a large interval. So we would like v and k not to be small, to be small not only in the neighborhood of the order 1 of 0 and mu n, but also in the large neighborhood, depending on k. If we don't know yet how we are going to choose k, it will be done later. So again, this is easy to construct. And the profile decomposition for our original sequence Vn implies then this profile decomposition for this more complicated family V and K, whereas the algebraic soliton is the same. What has changed is its position, which is now depends on K, and the remainder is also depends on K, but it still goes in H1 dot to zeros and goes to infinity. And what is important that this is uniform in K. And I recall you that our final goal is to arrive to contradiction, and to this end, we are going to study the monodromy matrix associated to this translated profile capital Un for some choice, from some suitable choice of k that will depend on n. And this choice of kn will come from the following lemma that you see here. So in this lemma, we fix theta, which is strictly less than pi and greater than m over 8. And using the profile decomposition that we can show that for all n sufficiently large and all k, if we consider the function a tilde associated to the potential v and k, it has a unique unique zero that I denote in this angle that's on the picture. And the angle argument zeta is less than pi greater than theta. That depends on k in principle. I denoted by zeta and k. It's a simple zero, and furthermore, it has this property: imaginary part of zeta and k goes to 0 uniformly with respect to k. And real part is bounded and separated from 0 uniformly with respect to any k. Again, I'm not going to discuss the proof of this lemma. It's an adaptation of the arguments we have used in the case of the real line, but the result is not at all surprising because our profile decomposition, what it says that morally our potential v and k is close to an algebraic soliton, and for algebraic soliton we have this embedded eigenvalue. So it's natural that we have an eigenvalue zeta and k with these properties. And the fact that there is only one eigenvalue, this comes from our bound on the number of the eigenvalues in the angles of this form, and because of these assumptions, that's all. Okay, the other thing is to prove it, but I am not discussing it here. Let me also mention that in the case of the real line, as soon as we can prove this, it's finished because it gives immediately contradiction. Indeed, in the case of the real line, we don't need to put the truncations, we don't need the k's, nothing of this. Our Vn here is just the rescaled solutions. So a tilde Vn is just a rescaled a tilde of initial data u0n. And if we assume that if we know that we have the zero, that zeta n times mu n gives us a zero for the a tilde associated to the initial data. And the zero goes, a real part of the zero goes to minus infinity. And it happens that this is impossible because we have a general bound that says that A tilde does not vanish in the region of this form real part of zeta less than minus some constant, with a constant that depends only on H1 norm of the potential. Well, now in periodic case, the thing's more complicated. We have to work more, and as I already mentioned, we are going to arrive to a contradiction. We are going to analyze the monodromy matrix of our translated periodic profile for some suitable choice of k. And to this end, first of all, we apply, we apply the Backlund transformation to our potential Vnk to remove this zero Znk. So we go from Vnk to a new potential Rn tilde k with the function A tilde for this new potential is related to the function is related to the function A tilde for the potential Vnk by this formula that shows clearly that we have removed the zero. And if we look on the momentum and the energy of the new potential, it's related to the momentum and the energy for the old potential by these explicit formulas, which are immediate from the asymptotics of the A tilde at infinity. And this gives us the bounds you see here. The momentum of the new potential and the energy of the new potential are bounded by mu n in the power minus 1 plus imaginary part of zeta n k. So this is because we have this bound for the momentum of Vnk and energy Vnk by the conservation of the periodic energy and periodic momentum, and by the fact that we put our truncation functions and the scale of mu n. Of 1 over mu n. And now if we consider the mass of the new potential, it's equal to the mass of the old potential minus 4 argument zeta n k. And so it's equal to m minus 4 pi plus small o of 1, just to say that it's for n large and for all k. It's strictly less than 4 pi, which allows us to apply the Guo-Wu inequality to conclude that H1 dot norm of the new potential squared is bounded by mu n into power minus 1 plus imaginary part of our zero Zn of k. And now, accordingly to the expression that we see in the right-hand side of this inequality, we are going to distinguish two cases. The first case will be the case where for all choices of k, the second term in the sum dominates the first one. So, and the second case, it will be when it's not, there are the k for which it's not true. So here you see it here. So in the first case is when if we take imaginary part zeta n k, we take mean over k, multiply par mu n, we go to infinity. And the second k, if up to the sequence, this quantity tends to some finite, has a finite limit. Now we are ready to fix k depending on n. So we fix k equal kn in such a way that in the first case kn goes to infinity, but slowly than this quantity. So this quantity divided by kn still goes to infinity. And in the second case, we just take the value for which this minima occurs. Well, and starting from this point, there will be no k, so we put Zn equals Zn of kn and so on. Okay, and now next step will be to study the monodromy matrix of the translated rescaled periodic profile capital Un with the translation which is given here. So this I denoted by Un tilde. And this can be done thanks to the smallness of the new potential in H1 dot, which allows to control the corresponding Yost function by a suitable WKB ansatz. And as soon as we control the Yost function of the new potential, we obtain also some information on the Yost function of the old formation potential, because one has an explicit formula that permits us to go from one set of functions to another. And so this gives us an explicit approximation for this monodromy matrix mu of n. Okay. Well, I'll try to finish rapidly. And so to arrive to contradiction now, we proceed differently depending on our regimes. In the first regime, we just consider, we work with a Floquet discriminant, and we show that the approximation we obtained give us something which is not, which contradicts the asymptotics, large time asymptotic, large lambda asymptotics of this object. And in the second case, it's more complicated. We have to consider the entire monodromy matrix. And again, we show that after zooming on the eigenvalues at n, we show that this thing has a limit with very special structure. And this structure happens, it turns out that this structure is impossible because of our result on locations of the large Dirichlet-Neyman eigenvalues that we have seen. Well, sorry, I have no time to explain the details. Thank you very much for your attention.
Very much for this very nice talk. We have time maybe for one or two questions in the audience. Yes.
No, we need the sorry.
So, if I know the Floquet discriminant and the Dirichlet eigenvalues and the Neumann eigenvalues,
Yeah.
do I know you?
Pardon?
Does the discriminant plus the Dirichlet eigenvalues plus the Neumann eigenvalues uniquely determine the potential?
I'm not considering this question. I don't know.
Thank you.
I use very for some properties that's very no.
Something like trace formula?
Yeah.
So this is still open. Peter.
Thank you. So I wanted to ask about the change from 8 pi to 12 pi. You mentioned at the beginning that you can go to 12 pi. So is it something like you apply your Beckman transformation?
Yes. Okay. This I can this I can explain. It's more. So in this picture, when you have 12 pi, you will have more eigenvalues here, and furthermore, they can be multiple. Well, there will be the eigenvalue generated by our profiles. These eigenvalues will have these properties like this, but there will be also eigenvalues generated by the remainder. This will be small, but we still have to take them into account because the mass of our remainder is not necessarily smaller than 4 pi. So we can't apply the control of Wu. So we have to remove first these small eigenvalues as well, so it becomes a little bit messy. And in addition, we also need to characterize the multi-soliton, the profiles, because in the case of the one profiles with a mass of 4 pi, we know that it's an algebraic soliton for which we have an explicit expression. But for larger masses, we don't know it. Okay.
Other questions? If not, we thank the speaker again.